This slide is the first slide of the part 3 of the presentation of the corrosion and corrosion control in water desalination of plants. This slide shows the types of corrosion observed in thermal tube modules, long tubes, MSF, water desalination plants, and how to control the crevice corrosion observed in these plants. One way to control the corrosion is to regular washing of nuts and bolts with fresh water to remove accumulated dust and seawater mist. Other option we have is the better use protective coatings or on-site molded polyurethane caps covering entire exposed section of nuts and bolts, holding plant to foundation to control crevice corrosion. This slide is a continuous of the corrosion observed in water desalination plants. Is talking about erosion corrosion. Two sterners from stage 1 to stage 12 with the long tube MSFWTP suffered erosion corrosion in the form of circumferential gouges and horizontal channels, reflecting the flow pattern of corrosive fluid along the tube external surfaces during operation. And this slide 54 is the actually slide as a part of the whole presentation, right? But what you can see is as the slides coming up, they explain it, right, how these patterns have appeared. Horizontal channels over tube surface starting from one end of the tube supports partition plates and extended to the other end and so on in the direction of vacuum. That's the other erosion corrosion observed in the different parts of the WDP MSF plants. This slide is the continuous of the previous slide. The erosion corrosion as observed in thermal MSF WTP. Identical horizontal channels were also observed on tube sternals well away from tube supports and partition plates at top tube surface, where white color with bluish greenish tinge deposits accumulated. All horizontal channels on tube sternals were in one orientation in the direction of vacuum. The external surface of tubes under white bluish green tinge color deposits looked spongy and were easy to chip off as shown in slide number 38 as a part of the overall presentation. But these spongy type deposits are shown in the next slide as a part of the part 3 presentation. This slide shows the erosion corrosion observed in thermal MSF WTP. Erosion corrosion observed in the form of horizontal channels and circumferential gouges in two modules, long tube MSF water desalination plant as explained in the previous slide. It continues of the erosion corrosion as shown in the previous slides. Erosion corrosion was also observed in the form of channels and surface roughness in product water drains inlet in MEE2 effects water desalination plant as shown in the slide 60 in the overall presentation, whereas these largest slides right will appear as we go on. Both effects in MEE were internally cladded with copper nickel 9010 to avoid CO2 erosion corrosion. Even their inlets were rounded off over a larger angle to avoid liquid erosion. This slide shows locations of erosion corrosion as observed in MEEWDP. The external surface of a protruded section of brine spray open and tube and internal surface of spray header adjacent to spray tube in MEEWDP plant exhibited erosion corrosion as shown in slide 59 as a part of the overall presentation, whereas right this slide will appear as we move on. Maintenance replaced threaded spray nozzle with open and welded tube protruding one open end into the spray header for securing weld to last longer as shown in the slide number 733 of the overall presentation, whereas it will appear as we go on. This slide shows locations of erosion corrosion observed in MSF water desalination plant. The erosion corrosion was notable at tube internals in state 12, heat rejection section at feed inlet in MSF cross tube water desalination plant in the form of elongated depressions in the direction of the flow. Although the feed water was being filtered through series of screens before entering state 12. In general, tube inlets and outlets in all stages suffered erosion corrosion, but the effect was more pronounced in state 12 tube internals. This slide shows location of erosion corrosion as observed in water desalination plants. Internally, cement-lined seawater intake pipeline exhibited erosion corrosion at welds after internal cement lining deteriorated during operation. This slide shows a pictorial representation of erosion corrosion location as observed in thermal MEE water desalination plant. It is a part of the spray header brine spray nozzle. You can see that the erosion corrosion is observed at the protruded tube weld right on the both sides of the spray header tube. Well, it was actually a technical flaw, made understanding that if we can protrude the spray header tube into the pipeline and do the welding, it will last longer. But on the contrary, the tube header spray tube lasted right within a very short period because of the erosion corrosion at the obstruction caused by the protruded end in the normal spray pipeline. This slide shows the location at where the erosion corrosion was observed in MEE water desalination plant. This slide shows causes of erosion corrosion observed in MEE water desalination plant. First cause was the high degree of flashings, uneven pressure equilibrium during operation, insufficient time given at startup for pressure to attain equilibrium. Decomposition of carbonates deposits into carbon dioxide, forming carbonic acid. Water turbulence and solid particles were considered responsible for causing erosion corrosion at tubes internals. This slide is the continuous of the causes of erosion corrosion as observed in MEE water desalination plant. Spray nozzles were replaced at site with identical material but with the unacceptable welded configuration. Spray nozzles were protruded into spray header by about 10 millimeter and welded from outside, as shown the previous slide and slide 73 of the overall presentation. The protrusion into the header pipe caused high degree of turbulence due to flow restriction, made nozzles and spray header undergo high degree of erosion corrosion. This slide shows how to control erosion corrosion in MSF WDP. High density polyethylene ferrules were used to control erosion corrosion at tube internals in MSF cross tube water desalination plant. Iron anodes were fixed on water box to control tubes internals erosion corrosion in two modules long tube MSF WTP. This slide shows the location of impingement corrosion observed in thermal MEE and MSF water desalination plants. Impingement corrosion was observed on spray nozzles and on top surface of tubes in the top two rows of heat exchangers in effect 1 and effect 2 in MEE WTP. It was also observed on inlet tube sheet and tubes supports. It is also observed on tubes located in the lower half of the tube bundle below demistress level MEE WDP. Two rows of tubes in a tube bundle were made from AISI 410 and AISI 430 to counter impingement attack and protect copper nickel 9010 tube sheet from galvanic corrosion in MEWTP. And this pigment corrosion was also observed on tubes externals in stage 1 to stage 4 in cross tube MSF WDP. This slide shows the cause of the impingement corrosion observed in thermal MEE WDP. During port screen failures, spray nozzles in these effects were becoming frequently clogged with seawater impurities, and maintenance turned spray nozzles to spray tubes and permitted the seawater to fall freely on tubes, causing impingement corrosion on top surface of tubes in top two rows in MEE water DP. This slide shows the observation as a part of impingement corrosion in thermal MEE WDP. Outer surface of all tubes was covered with reddish brown, loosely adhered powdery layer and tenacious black passive layer with discrete white stains, except the weaker regions which looked slightly jagged and light brownish in MEEWDP. Thin, strongly adherent, tenacious black passive layer on the tube surface protected tubes from further corrosion. Thick, black, quite adherent scale was vivid at discrete spots but was more evident closer to tube supports. And the area under tube supports was clean but covered with tenacious black passive layer. This slide continues with the observation made as a part of impingement corrosion in thermal MEE water desalination plant. Closer to inlet tube sheet and tube supports, the outer surface exhibited circumferential, deeply gouged impressions with deeper pits in MEWDP. Gouges were more pronounced near the inlet end because of higher temperature differential as compared to the outlet. This slide is the continuation of the observations made as a part of impingement corrosion in thermal MEEWTP. Localized dissolution with deeper pits was more pronounced on one side of the tube, the side that received direct condensate impact and receded as moved along the surface of the tube to opposite side. Localized dissolution depicted the flow pattern of the condensate around the tube circumference. Distillate vapors saturated with corrosive gases condensed at the tube sheet and tube supports, dripped along the wall to adjacent tubes and caused localized attack. This slide shows observations made as a part of impingement corrosion in thermal MEE WDP. The badly affected area also exhibited circular light brownish spots depicting hard impingement points on tube surface. Light brownish circular spots, but less defined, were visible beyond the second tube supports from inlet end. The impingement impressions on these tube ends were caused by steam vapor laden with water droplets. During inspection, demisters were found distorted, dislocated, fouled, allowed water droplets to pass along the steam vapors. This slide shows the observations and recommendations made during the impingement corrosion in thermal MEWDP. The solution of tubes externals were localized, caused by the presence of carbon dioxide trapped in escaped water droplets. It was recommended to replace the misters and fix them properly to solve impingement corrosion and discrete dissolution of tubes externals. This slide shows causes of impingement corrosion in thermal MEEWDP. They replaced spray nozzles with the spray tubes. Improper welding strategy distorted, dislocated, folded, dislodged, and crumpled the misters, allowed water droplets to escape along with water vapors. The presence of carbon dioxide in dropping condensate was also a part of the cause of the impingement corrosion. This slide shows how to control impingement corrosion in MEEWDP. It was recommended to revert to spray nozzles as per original design and replace the misters and fix them properly. This slide shows the configuration of the welding technique used that caused impingement corrosion in flow directions at the spray header spray tube protrusion. You see that how the internal surface were impinged during operation in the direction of the flow. This is a brine spray system where the spray tubes were protruded into the spray header and welded in there amid an opinion that the welding in this configuration will prevent the deterioration of the tubes, whereas deteriorated very fast because of the impingement corrosion at the protruded tube ends. This slide shows intergranular corrosion as observed in thermal MEEWDP. AISI 316 stainless steel tubes under and adjacent to tube supports in tube bundle in a reboiler in two effects MEEWDP underwent intergranular corrosion. The shell was made of carbon steel like the original tube bundle. Slide 75 shows a configuration of the reboiler as a part of the overall presentation, but this slide will comes up as we move on. Reboiler was a shell U-tube type heat exchanger to generate medium pressure steam for a thermocompressor unit in MEWDP. Operations were adding 10% caustic solution into the feed water to raise this pH to the desired level. This slide shows the configuration of the reboiler where the intergranular corrosion was observed during operation. The configuration is self-explanatory, right, to show that how the HP stream enters from where the LP steam escapes and from where the condensate comes out and where the makeup water is added and where the brine is discharged.